Hello and welcome back. Now we want to talk about how we can learn sequences with neural networks. Most of this is done with attention and transformer networks these days, but in order to understand those better, we'll start with recurrent networks and long short-term memory networks. Before we start with those, let's recap how feed-forward networks work. Remember that we have sort of a linear information flow. So the information enters the network via the input layer, for example from our featured variables, then passes through one or more hidden layers. This is like the deep in deep learning, and we finally have an output layer. So all the nodes are connected only in one way, towards the output from the input. So the information flow is always from left to right. But how can we now learn sequences? Feed-forward networks learn direct mappings between input and output, our feature variables x to a predictor y hat. But this is not enough for sequences. For example, consider the sentence, the sun is in the, and we would naturally put sky there. Or, I grew up in Germany, I'm fluent in German. Or other examples, for example, could be time series data. We could also have related sequences like a machine translation. The German sentence might be, ich studiere Materialwissenschaften, and we want to get to the English sequence, I study material science. On a very abstract level, what we want to have is a sequence-to-sequence setup. So, for example, we start with our German sentence, and this is some sort of representation of input variables x. More generally, we will consider these as tokens that could be words or parts of words or pixels even. We put this into some sort of encoder that generates us in some intermediate state z. Some decoder takes such an intermediate state and outputs a different sequence that could, for example, be our English sentence. So how do we do all of that? The idea behind recurrent network is that we introduce backward connections. In the forward network we always had input layer, hidden layer or hidden layers output, and now we have the output of a neuron goes back to the input of the same neuron, or the same for groups or layers of neurons. And this essentially allows us to learn sequences like time series, languages or whatever. This also means we introduce some sort of a recursion, because the input at step time t is our input variables x at this time t plus the previous time step t minus y. So if we compare this with the output of the previous node, we still have our activation function. Now our inputs at times t with our weight matrix and the output of the previous recursion, or graphically there, we pass the input through the neuron to the output, and then we branch out, and via the red arrow we go back to the input, and then the next in the sequence will receive both the input and the previous output. How do we train a recurrent neural network? Essentially it is trained with backpropagation, same as feed-forward networks, but we need to disentangle or unroll these recursions. This is called BTT, backpropagation through time. There are some challenges with this, of course. We need to have many recursions for long sequences to be able to capture their essence, and this leads to large unrolled networks because we have to undo the sequence. And this makes it, although in principle the same with backpropagation as feed-forward network, but in practice it becomes more tricky. We can extend the simple feedback loop with a memory cell. Here we can introduce a hidden state. So this is some function f that modifies the output of the neuron before sending it back. So this hidden cell, the hidden state, h of t, is some sort of function that depends also on the previous outputs it received and on the input. And this allows us to introduce some sort of memory from earlier elements in the sequence. So these memory cells essentially allow us to have longer sequences, because now we can decide what to remember, the relevant part of the sequence, and of course we need some sort of mechanism to decide what is relevant, but we can also decide what to forget. Now let's look at a little more detail. We started with sequence to sequence, and now let's look at this encoder in a bit more detail. So each encoder is comprised of a cell, and we need to look at how this cell is set up later. And each of these cells takes some part of these input tokens. And all of these cells are connected with the hidden states. And at the end, it is passed into an intermediate state. The decoder sort of reverses all of that. We have the hidden states as input, and outcomes from the decoder are desired output. For example, we start with X with a German sentence, and with Y we obtain the English sentence. The long short-term memory, or LSTM for short, is one of these very effective memory cells. So this is one of these building blocks that we have seen in the decoder and encoder part. And the key idea between the setup here is that we can decide what to forget and what to remember in long sequences. So we introduce a very efficient memory. And you can see here on the right that such an LSTM cell is quite complex. You have many elements to go with this, right? And this is one building block that goes into this encoder and decoder. These LSTM cells are largely superseded by the attention transformer these days, but we need to understand how they work in principle before we can move on. So let's recap about sequences. Let's consider a complex sequence. Even for short sequences we can have complex dependencies. For example, a Spanish-English translation. You can see the sentences here. There's a nice illustration from the TensorFlow manual which I've taken here. So you can see that the Spanish and the English are very similar, but not quite the same, apart of course from the vocabulary. You can still see that the sort of the structure of the sentence is very similar between the two of them. But of course that doesn't necessarily have to be this way. The sequence in different languages could be very different, or even reverse in order. If we have longer sequences, we also require our system that we focus more on the context. So that means which tokens, like words for example, are relevant for which part of the sequence. And you can see this on the matrix on the right, where you have the English and the Spanish sentence on the axis, and you can see that there is sort of a diagonal structure, but already in this example we can see that it diverges from a single diagonal. Of course, now it's easy to imagine that if you have long sequences or more complex structure, that this matrix becomes even more complicated, and this essentially is one of the challenges that we encounter in sequence learning. So let's move towards attention. What is the basic idea of attention? The idea is that different parts of the sequence have more relevance to each other than other parts of the sequences. So let's consider the sentence, the woman is driving a red car. We can, for example, say that red and car belong together because red directly describes the car. So this is something what we would call with high attention. Also, driving and car are quite closely related because the car needs to be driven or maybe even drive itself in the future. But driving and car are very related. Whereas driving and red are not so much related. You can drive a blue car, for example, and it wouldn't make much of a difference to the sentence. So there is a different level of importance in the relationship between those words. We drive, we expect a stronger connection to car and red, as we've just seen, and with red is more related to car than driving. And attention is then some mechanism that allows us to learn essentially importance weight. And that allows us to determine what is related to what and how strong is that connection. So let's move now from simple RNN and keep this picture in mind. This is what we had before. We have the encoder that was comprised of various cells, for example an LSTM memory cell, and a range of those, depending on our input tokens, would be our encoder that outputs intermediate state and puts it into a decoder with a similar architecture. Now, let's move this a bit apart, because you've seen that we have only one intermediate stage. This one intermediate hidden stage is something we say, why would we only use one? Why could we not have more that are related? And this is something we can call a context vector. So the encoder and decoder part are more or less the same as we've seen previously, with one example extension here, that in the decoder we have now hidden states going in both directions, like a bidirectional encoder. But in principle we don't really touch those two. but we modify the way those two interact. Instead of having just one hidden state from the last cell of the encoder into the first cell of the decoder, we now put all of these from each cell of the encoder to some cell in the decoder where it's relevant. So now, of course, we need to decide how we do this, right? We could just have them all with the same weight. All hidden states hi come with the same weight, but we've seen from the motivation of attention that this is not a good idea. We want to find combinations that are particularly relevant for this part of the sequence. And this is what the key idea behind the attention mechanism, that we define some sort of weight alpha. So on a high level, alpha is some sort of alignment between the input and the output tokens. Of course, we need to define in more detail what that means. We can rephrase the problem in saying the alignment is some sort of score, and we take the softmax function. So the denominator and numerator with the exponential function, this is the softmax that essentially transforms the output in the range between 0 and 1. And then we use some sort of score function between the sequences. Of course, now we've just shifted the problem from finding an alignment function to a score function. But to recap, right, we have the context vector. So for each output, we consider all the hidden states of the encoder and apply some sort of weight determining its importance. And these weights are the alignment weights. And that describes how well does the output input x and the output at some position in the sequence match. And we express this as sort of a probability, or rather it's not a normalized probability, as some sort of value between 0 and 1 over some score function. So now the idea is that we make the score function learnable. And what we mean by this is that it's not a handcrafted feature, but we use, for example, a small neural network. And this then leads us to the basic self-attention, right? So recurrent networks in attention improve on long sequences, but they have these RNN architectures. And self-attention is then one step moving to the transformer architecture. And self-attention is the attention mechanism of a sequence with itself. So instead of using two different sequences x and y, now we have the attention of an input vector with the input vector itself. And so we can provide a context vector defined on these, right? So Z is now this context vector with alignment weights on the input. And the simplest way we can have alignment weights is this dot product between the input sequence, here omega ij. So the transpose of the vector x with itself. And now we take the softmax function, and that's like the simplest version of a alignment weight that we could have. Before we move on, we need to recap on some terminology, query, key, and value, because they play an integral part in the terminology used in transformer architecture. Let's keep it on a very simple level and imagine you're using a search engine like Bing, Google, or others. So what the query is the text that you type in, and the output is the value. This is what you see. And what happens behind the scene is that the query is translated to some sort of set of keys and then matched against the record that are behind the search engine. Of course, this is more complex in detail, but the idea is that you translate the query into keys, you match the keys into what you have stored as a result of your previous web crawling, and then return those where the key matches, and this is the output you receive. Right, so now we move towards the attention and transformer networks. We're starting with query and key. Step 1 is to determine Q for query and key for key, and they both refer to the input sequence. The question remains, what is the best key for a given query Q? And instead of using the elements directly, as we have done with the simple self-attention in the previous example, we first transform them into a vector space. And we do this by adding learnable weights to them, WQ and WK. So that means essentially we have another neural network here, right? So we have an element xi, transform it with a query key. We have an element xj, transform it with a query key. So instead of using the input sequence x directly, we have now two sequences based on x Q and K in capitals, here given on the right, that differ from the input sequence by those learnable weights. And now we do essentially the same thing that we have done, and this leads us to the attention mechanism. Now we provide some sort of similarity score between capital Q and capital K, and you can see that on the right hand side the omega definition is almost the same as with the simplest self-attention mechanism that we had before, but now we use the capital Q and the capital K, which is the input X modified each with a weight matrix, one for Q, one for K. And then we do the same thing and calculate the softmax, and it's custom to normalize this by the number of dimensions of the key. Right, and here we have essentially the same thing. Now we attach attention value, we call the simple self-attention again, right? We now don't base it on X again, but we have another weight matrix for V, for the values, and this creates our context vector for the self-attention with learnable weights. Now, let's summarize this again. The key idea between the scaled dot attention, this is what's underlying all of the transformer architecture, is that we use the attention between the sequences X. But instead of using these attention directly, as we have done with the simple self-attention, we modify it 3 times. One for Q, one for K, one for V. And now we do the same thing as we have done when moving from the RNN to the simple self-attention. We first have these weights omega, for one for Q and K, and the same then later for the product with V. Then we use this to define our alignment or our attention. These omegas go into the softmax function, normalized by the square root of the number of dimensions, and this then defines our context vector Z. And all of that goes back into the softmax function, and this is what you can see as a compact formula on the right. So the softmax of Q times K transpose normalized times V. This is essentially the scaled dot attention that is the fundamental building block of the transformer architecture. How do you build such a transformer now? And of course this is when all the optimizations of the architecture go. You have the image on the left hand side, the small one with K, Q and V. Remember this, right? This becomes now one of these building blocks, similar to what a neuron would be in like a feed-forward network. So you have K, V and Q, put this into a linear layer, and then you have the scaled dot attention mechanism in multiple variations. In the end, you need to bring all of that together and, for example, have a linear layer for classification again. And then the name of the game is to build a transformer-based architecture that is particularly sufficient and efficient for a given application task. One word on position encoding, because nowhere in this attention block we have made any assumption on the order of the tokens, right? We have always assumed that the sentence has some sort of structure in it. When we talked about, for example, the translation of a German to an English sentence, but we haven't actually encountered any way of making the order of the words explicit. So as the basic version goes, it doesn't know about the word order, and we could put this, for example, if you modulate it with the sine or cosine function, we can encode some positioning into what gets used in the transformer architecture. There are of course other ways to encode this, and this makes it easier for the network to learn how different parts of the sequence relate to each other.